Thank you so much for joining me today. I'm really excited. Hope you all enjoyed the keynote. And now we're going to dig. So DeWitt's keynote is always really deep stuff, or at least that's what's rumored to be. And maybe not everyone agrees. But anyway, we're going to dig a little deeper now into the actual product that we all use on a daily basis. Quick warning. I know you're all very excited about Denali, or SQL Server 2012, as it's now called. But what we're going to talk about today pertains to SQL Server 2008, 2008 R2, mostly to 2005 as well. Some of this will change in Denali, not very much. I know what the changes are. They're not huge, but if you want Denali information, you might want to get up and find another session to attend. Most of this is undocumented stuff. No guarantees from Microsoft that this will be supported going forward. This is a 500 level talk. That means different things to different people. Bob Ward opens his debugger. I'm not going to open a debugger, but I am going to go deep into internals. I'm going to make use of some settings that you may or may not have seen before, and I'm going to show you a bunch of query hints. Now, a lot of DBAs I know are offended by the mere idea of query hints, and a lot of people think they're going to break in the production environment. Well, they may, and I'm going to make no guarantees that I won't break anything in your production environment. So if this offends you, again, you have a little time, go find another session. If you want to find out how to use this stuff to drive extreme performance, stick around. I see no one's leaving, so that's good. Let's chat about SQL Server a bit. Now, sometimes when SQL Server is working on a query, it needs to do something, and it needs some space to do that, a little scratch space in which to work. And so it goes out and gets some scratch space and does what it needs to do. And sometimes, unfortunately, there's just not enough space, and SQL Server needs to find somewhere else to put the information. And by the way, if you ever repeat this experiment at home, on your kitchen floor, a washable Crayola marker is a much better choice than a Sharpie. Trust me on this. So SQL Server needs to take this space and do something. And that's one aspect of what we're going to talk about. Now, I want you to think about SQL Server for the remainder of this talk as like a big birthday party. And everyone comes to the birthday party, and they put on their party hats and start having fun. And after the cake and ice cream is served, you know what time it is? It's activity time. Woo! So what we hope will happen is we'll put out a bunch of activities, and all the kids will share and have fun and work and play nice together. But that's not always what happens, is it? Sometimes we don't have enough toys for all the kids, and they have to fight for something. And when this happens, either at the birthday party or in SQL Server, the inevitable conclusion is that, well, one kid can win, and the other has to sit in the back waiting. Never very much fun. So this talk is all about how we can work towards avoiding this situation. And can't all of our processes just get along? Wouldn't that be wonderful? Well, before we continue, a little bit about me. I've written a few books, SQL Server 2008 Internals, Expert SQL Server 2005 Development. Hopefully you've been able to pick one of those up at some point. I do a lot of training and speaking at various conferences, such as this one, TechEd, SQL Connections, and so on. I run a training company called Data Education. Hopefully you'll check out some of our courses. I also run a website called SQLblog.com. We have about 40 very high-end bloggers on that site. Please check it out if you get a chance. And if you'd like to reach me for any reason, my email address is at the bottom of the screen, or you can just find the contact logo on my blog and contact me from there. So here is how we will spend our time together today. First, we'll discuss the basics. What is Workspace Memory? Why should you care? Then we'll get into what happens when there's not enough resources around and that fight needs to occur. And finally, we'll get into establishing balance, making everyone play nice together, forcing them to play nice together if we need to. So let's get into it. Every single query that runs in SQL Server needs memory. There's compile memory. There's memory around infrastructure for every iterator. Every iterator has state, and there are, of course, all of the rows that are flowing through these iterators, and that all requires some memory. Certain iterators, however, need a bit more memory, and we refer to these as the memory-consuming iterators. It's a small handful of iterators that need a lot more memory than all the other iterators. And when this memory is needed, the query has to acquire something called a Workspace Memory grant. By the way, Workspace Memory is also known as query memory. Those two are interchangeable terms, and you'll probably hear me switch back and forth throughout the talk since I can never keep them straight in my head. And my laptop is now crashed, so I'm going to reboot it. Not due to the demos from this talk, however. Just FYI. OK. 1 second, sorry. So here are the memory-consuming iterators. As you can see, there's only about 7 of them. HashMatch iterators, both flavors. Hash and aggregate, sort and top end, and the 3 exchange or parallelism iterators, distribute, gather, and repartition. And that's it. All of the other iterators require just basic infrastructure and state memory. These ones are the ones that do the heavy lifting and can require a lot more memory at runtime. So if you think about memory, I'm sure that you've all been told or thought at some point you can never have enough memory in SQL Server. And that's absolutely true, especially when it comes to workspace memory. Now, the workspace memory, at least as of SQL Server 2008 and R2, comes from the buffer pool. So this is the area where all of your database pages are cached as they're read into memory. And as workspace memory is needed by these iterators, they will take that memory out of the buffer pool and start reusing it. And if you are using a lot of sorts, hashes, and exchanges, this area, the workspace memory area, can use up to 75% of your buffer pool allocation. So that can really add up. That can really mean a lot of shifting of resources back and forth between pools in your SQL Server. And that may or may not be a good thing for your workload. So this is something you want to start keeping in mind as we talk about this. Now, the way that this is handled is that before a query can run, it has to go through an optimization process. And during optimization, the query optimizer comes up with something called an ideal grant. Now, this is the amount of memory that would be required if all of the memory-consuming iterators in the query were able to be completely processed in memory without any spill to disk. We'll get into spills to disk in just a bit. Now, if the ideal grant is too high, at runtime, it can be scaled back based on resource governor, resource pool settings, or other runtime settings. And we'll talk about how that works as well. So at compile time, once again, the query optimizer has to come up with this ideal grant. And it does this using the metrics that it has available to it. These are statistics, row counts, estimates, as well as data sizes. And it comes up with basically a size of the input set into each iterator. And this is based on the estimated row count, the estimated row size. And it comes up with the amount of memory that it believes, remember, believes is the key word here. These are estimates, will be required at runtime to do everything in memory. Now, that's only an estimate. And I just want to stress that one more time. I'm always like to stress that cost-based optimization is all about estimates. And what happens at runtime may or may not coincide with what happens at compile time. So what we could do is take all the grants and add them up for each iterator. So you have 3 sorts. Each sort requires a 100 meg grant. You could add those 3 up and come up with a 300 meg total grant. But that wouldn't be too efficient. So what the SQL Server team did is they thought through this a bit more and realized that some of the iterators can actually share memory. Each iterator has a build side and a utilization side. Next slide, please. And the memory requirement for the build tends to be much greater than for the utilization side. For example, sort will use about twice as much memory during the actual process of sorting the data as it needs to store the sorted data once that sort is finished. So it will allocate that big, huge chunk of memory at build time, and then as soon as the sort is finished and the upstream iterators can start consuming those rows, it can free up half that memory and let those upstream iterators start taking it in. And this is called a memory fraction. We can actually look in the query plan, and for each memory-consuming iterator, we can see what its fraction is. And the fraction is the way that child iterators relate to parent iterators in terms of memory utilization and sharing. And all of this goes into figuring out the final grant. So the query optimizer tries to produce a minimum grant such that all of the iterators, based on how much memory they're sharing, can use the optimal amount of memory at runtime. So once the optimizer has done its job, it's time for the query to run. And a few different things happen at this point. First of all, the query is categorized based on its importance in the resource governor workload group that is running it. And you might be saying to yourself, well, I haven't created any workload groups, so therefore that doesn't apply to me. Untrue. There are two workload groups that ship inside of SQL Server, a default group and an internal group. And all of your queries, unbeknownst to you or maybe known to you, are running there right now with normal level of importance. Now, if you modify that or if you create some new workload groups, you can control how things get allocated and how things get categorized. And once the workload group has been determined, the query is further categorized, and the optimizer looks at the query cost as well as the size of the grant and takes the importance and that second categorization, and it has a number of queues. And all these queues sit inside of a gateway called the resource semaphore. Now, a semaphore is a computer science abstraction of basically an area into which only a certain number of threads can get at any given time. The resource semaphore is a bit more dynamic than a lot of semaphores you'll see in other languages, in that it's controlled not by a hard number of threads coming in, but rather a dynamic amount of memory that may or may not be available. So the resource semaphore's job is to control how many threads and which threads are using memory at any given time and how much they can acquire. So if a query goes into the resource semaphore and there's not enough memory, it has to sit there and wait and wait and wait until finally, hopefully, there will be enough memory. So, as I mentioned before, there are queues inside the resource semaphore, and the way that this is divvied up is that each resource pool that you create, or there are, again, two default ones that ship with SQL Server, has two of these semaphores. There's a small semaphore, and every query with a low cost, less than 3, and a very small grant size of less than 5 megs will go right into the small semaphore. And the small semaphore is prioritized. The idea is that small queries should be able to go in, run really, really quickly, and get out, whereas large queries are going to take longer to run anyway. So if they have to wait for a little memory, that's okay. You probably won't notice. Well, that's the idea. We'll see if that actually lines up with reality in just a bit. So the small semaphore is for the small stuff, and the large semaphore is for everything else. Now, both of these semaphores have 3 internal sets of queues. A low importance one, a medium importance one, and a high importance one. And these align with the importance level specified in the resource governor workload group. So the small semaphore has just one set of these 3 low, medium, and high importance queues, and there's priority there. So if you have a bunch of high importance queries running, and there's not enough memory left, the resource semaphore is not going to start running those medium importance queries until the high importance ones finish, until that queue up at the top clears out. Now in the large semaphore, it gets a little bit more complex. Instead of just 3 queues, there are 3 sets, each of 5 queues. So there's 1 queue for everything of query cost less than 10, and then it goes up by an order of magnitude, 10 to 99, 100 to 999, 1,000, and then finally your massive 10,000 cost queries. And these are the really, really big queries that will take a long, long time to run. So once again, these are prioritized. The smaller cost queries are actually prioritized over the larger cost huge queries. The idea being, once again, we'll get the small guys out of the way first, then allocate the resources to let the big queries through. So let's look at an example of this. If we have 10 queries in the 100 to 999 cost queue, and a query hits the 10,000 cost queue, but let's say that that query costs 10,000 but uses very little memory. And I'll show you an example of this in a few minutes. That query will actually sit there waiting until all of the small queries are finished. And again, the idea is to clear out those resources and improve concurrency, but unfortunately, and this is why we need to care about this, sometimes this can actually reduce concurrency in our environment. If you have a few large queries trying to contend with a number of small queries, you can wind up with a situation that's almost starvation. So we need to understand how to control this. And one of the ways we can control this is through what's called a query timeout. After some time, your query, after it's been waiting, will eventually time out. And at that timeout, depending on the state of the server, it'll either start running or throw an exception. Guess which one we want to have happen? The exception, of course. Come on. So here's how it works. First of all, queries will sit in that semaphore, and they will not start until 150% of the available, of the requested query memory, that memory is available. Why 150%? Not 100%? Once again, the goal is to create or maximize concurrency. And so the idea is that by leaving a bit of headroom, we can send more stuff in later if needed, rather than taking the entire grant and maybe using up all the available memory. The exception to this is when this timeout occurs. So what happens is, by default, a query will sit in the queue and wait for 25 times of whatever the query cost is in seconds, up to a maximum of 24 hours. It can sit there waiting in that queue. Now, once that timeout period hits, two things can happen if there's not enough available memory. Thing one that can happen is that the grant will be reduced all the way down to the bare minimum required grant for that query, which means lots and lots of disk activity will occur. And the query may take a long time to run, so it can sit there for actually 24 hours and then have no memory in which to run and sit there doing its best. Or you'll see this error, 8645, which is a fairly severe level 17 error that says there wasn't even enough memory to start with the minimum grant. Goodbye, thank you for playing. So we really want to start monitoring this and making sure this is not happening in our systems, and that we don't have queries waiting 24 hours before they can even begin, only to be hit with a nasty error. This is not a good thing to have happen. Trust me on this. Excellent question. Question is, if a query is waiting and other higher priority queries come in, will the query that was already waiting continue waiting? The answer is yes. So if I have a query that's low priority, and it's sitting there waiting behind a bunch of medium priority queries, and more medium priority queries come in, that low priority query keeps waiting. It only exits that wait state when either there's no more medium importance queries, or they're not taking up all the memory, or the timeout hits. The query wait type will be resource semaphore. We'll talk about that in just a moment. Okay. So, several different configuration options here that pertain to this area. First of all, in SP configure, max server memory. Since the maximum workspace memory grant is taken out of the B pool, max server memory configures the B pool, and that directly influences this. Second, query wait. If you want to override that default 25-time query cost, you can do it either here at the server level, or you can do it down in the resource governor at the workload group level using the request memory grant timeout seconds option. Same thing, different levels of granularity. Min memory per query. The default here, so any query that gets a grant is going to have some minimum grant and then more memory on top of that. Now, by default, every query that gets a grant will have a minimum of 1 meg. If you want to bump that up, I don't actually know why you'd want to bump that up, but if you have a use case for this, you can tweak the min memory per query in KB option at the server level. And you can say, for example, I'd like every query that comes in and that needs a grant to get 200 megs. Probably not a good idea, because now all your queries will start getting 200 megs, and unless you have a few terabytes on your server, you'll quickly run out of resources. But if you want to play that game, by all means. Now, down at the resource pool level, you can specify a min and max memory percent. And what you can do is actually specify that given resource pool, using these settings, won't have to share memory with all the other resource pools. So you can create kind of virtual sandboxes for your resource pools and allow queries in each pool to have dedicated memory. And this is one way we can control things and improve concurrency when we have known workloads coming in. Down at the the workload group level, we can specify the importance. So the queries coming in from the CEO, maybe, can be prioritized over those coming in from your marketing manager. Always a good move. We can also specify, again, the timeout seconds and the maximum memory grant percentage. Now, by default, queries and memories will be granted at most 25% of the available query memory. We can tweak this either up or down as needed in order to improve either concurrency or make more memory available to our queries. So lots and lots of different options here. Now on the monitoring side, we also have to delve in a bit. First of all, if we want to monitor this memory, the best way to do it is to use DBCC memory status, and there are two different areas that you need to look at. There's the small query memory objects and the large query memory objects, or just the query memory objects. And each pool has two of these counters inside a DBCC memory status, and they correspond, of course, to the two resource semaphores. There's also a DMB, System Exec Query Resource Semaphores, which contains 1 row per semaphore, just kind of a different view of the world. DBCC memory status actually contains more interesting information most of the time than the DMB, unfortunately. Then we have a view called System Exec Query Memory Grants. This view contains information about all of the queries that are either waiting for a grant or have had memory granted and are still running. And so this is where you can look and find out which queries are waiting on memory, how much memory they're waiting on, and which queries are using the memory, keeping the other queries from being able to get their memory. So this one is invaluable when you're monitoring this stuff. And then finally, SysTMOS waiting tasks. If you look for the resource semaphore wait, this is the wait type that all the queries that can't get memory right away will be sitting on and waiting and waiting and waiting. So let's jump out, check some of this out here. Okay, so over in Management Studio. Oh, it didn't work. Let's try. How's that? Better? Okay, cool. So jump into AdventureWorks. And the first thing I'm going to do is I am going to configure max server memory on my server to a nice even number, or my laptop. I like to call it my server, but it's a 15-inch screen. What can I say? I'm going to configure it to 1,000 megs, nice even numbers, just so that we can have some nice, good numbers to play with. And I'm going to reconfigure that. And max server memory, just in case you haven't really delved in here, only has to do with the memory configured for the buffer pool. There are other pools outside max server memory. So I definitely recommend reading up on this if that came as a surprise to you. So now I have 1,000 megs in my buffer pool, and let's verify using DBCC memory status. So we'll look for 3 different things. We'll look for the buffer pool area, which we hope to be 128,000 pages. Look for the default memory pool, same thing, 128,000 pages. And then we can start looking at our query memory areas, query memory objects and small query memory objects. So let's jump in there. And I always love looking at DBCC memory status, like where's Waldo? Scrolling through and trying to find the right area. Okay, so there's our buffer pool. And you can see we hit our target, 128,000 pages. My configuration worked. Excellent. And now let's go down and try to find the query memory objects for the default pool. Here we go. So 91371 available, nothing's running. No requests are waiting for anything, so we're all set. For small memory objects, we have reserved 4809. And if we take those numbers and we add them up, select 91371 plus 4809, and we take that and we divide it by 128,000.0, we get, anyone good at math? Good man, 75%. If I had a book to give you or something, I would. Unfortunately, I don't. So 75% of the vpool memory has been allocated for query memory. And so we can see that what I said on the slides is true. Cool. Now, let's go. So the question is, if you have multiple resource pools, will it total to 75%? And the way it works is it depends on how you've set those resource pool min and max settings. Basically, you need to configure those so that memory, well, if you configure them the wrong way, let's put it this way, memory will be shared among the pools. And when there's pressure, the pools will contend for that memory. If you configure them the right way, the percentages will actually match up to the percent allotted to each pool. So if you have one pool with 50%, the other pool with 50%, then your workspace memory grant will be equally split across the two pools. Right. Okay. So let's take a look at an actual plan here. And I'll show you how to look at the memory grant. Include actual execution plan. So this is a simple query. We're selecting 1,000 rows from production.transaction history in the EventureWorks database, ordering by a column that's not indexed. And I'm forcing a max stop one hit just to make things nice and simple. And I'm going to hit Control L. And what we can see is that we get a clustered index scan followed by a sort. Let me just zoom it up so that I can, where's zoom it? Zoom it. Run. Excellent. Okay. Kevin Klein, yeah, he came to my user group and I put up a picture of this other Kevin Klein to embarrass him, and it was nice. It worked out well. So, anyway, I digress. So we have a clustered index scan, and the estimate is that 5.9 megs is going to come into this sort iterator and have to be sorted. And based on that estimate, the sort iterator is going to allocate some memory and sort the data and then return the top 1,000 to us. So let's go ahead and hit F5 here. Okay, so the query just ran. And now we can go out and in an actual query plan, so the one that we were looking at before was the estimated query plan. In the actual query plan, we have a little bit more information. If we hover over here, we can see the actual number of rows that pass through. And if we hover over the select iterator, we can see the memory grant, the actual memory grant that was granted. So as you can see, the memory grant was 13560. This number is in KB. So 13 megs were granted for sorting 5.9 megs of data. So as you can see, sorts can get pretty big, about 200% of the input data size. So definitely something you want to think about. If your queries are doing a bunch of large sorts, your buffer pool is going to be continually losing pages in order to handle this information. And then latter queries, you're going to have to reread data off of disk. Something to think about in terms of concurrency and your overall workload. So let's take another look. Now remember I said that the iterators in a plan can share memory. So here I've created a query, and what it does is it selects 100 rows from production.transaction history, orders them one way, selects 50 from there, orders it another way, selects 20 from there, orders it a third way. And so what we wind up with is 1, 2, 3 sorts in a row. And this is, of course, a meaningless query. But what I want to show you is if you click on one of these iterators, hit F4, the little window pops up. And in there is something called memory fractions. Let me click on this. Now I'm looking at the memory fraction for the first sort. And what we can see is that the input fraction is 1. That means the entire set of memory is available and comes in when that sort goes into its build phase. And when it's done with its build phase, half of the memory that it used, the output amount, is available for upstream iterators to go ahead and use. Okay? Now when we look at the second one, I'm going to go ahead and click here. Its input fraction of the memory is half, because it took half from the parent. And its output is also half, because, again, once it's done with its build phase, it can give up half of its memory and send it on upstream. And the final iterator once again has an input of half, because it takes half the memory from the build of the prior iterator. And its output is 1, because there are no more memory-consuming iterators upstream. So as you're looking through query plans that have these memory-consuming iterators, and you want to understand the memory relationship between these iterators, you can start looking at these fractions. It's not always this simple with 0.5s and 1s and things like that. As you get into hash matches especially, you'll get some very interesting numbers, because they don't align so nicely with 200% of the data and so on. But this will give you some idea as you go through your plans of how that memory is actually being used and where it's being allotted and what the query optimizer actually thinks is going to happen in terms of those grant requirements. So the question is, if the first one is 0.5, is the second one half of that 0.5? Or is it something else? So these are actually relationships between the iterators. It has nothing to do with the actual overall grant. It's a relationship between the first iterator and the second. So the first iterator can output half of its grant, and then the second iterator can take half the grant from the prior iterator, and so on. Does that answer your question? Sorry? Well, it's not necessarily a quarter, because it depends on, it's not the same memory. Remember, it applies to each iterator. So it depends on how much each of those iterators are going to be using. Right? Any other clarifications I can make on that? Okay, fantastic. So let's move on. And let's take a look at system exec query memory grants. And we're not going to see anything in here, because nothing's running. But let's run something. And what I've done here is I'm taking 1,000,000 rows from a table called Big Transaction History, which is a version of AdventureWorks.transaction history that I've grown into a 30 million row table. And I'm going to pop that into a top 1,000 sort, ordered by the actual cost column. So we're going to sort 1,000,000 rows on one thread. And what we're going to see is that we got a memory grant. Excellent. So session 52 was granted some memory. It was granted 92 megs, which is the same amount of memory requested. Now, it only required, at minimum, 512K to run. That's the minimum requirement for sort. Each of the iterators has a minimum required space. Sort happens to be 512. But luckily, there was plenty of memory around. So it was able to be granted the full 92 megs it asked for, and it went ahead and used it all up. The query has a cost of 132. And were it queuing, these things would all be populated, and we'll talk about what those look like. Now, as I pump up the number of input rows, so let's take a look at the plan here. Basically, it's an index scan, estimated 1,000,000 rows, goes into the top, and then we sort 1,000,000 rows to find the top 1,000. Now, as I pump up that number, let's say to 1.2 million, I can go over here and look at the memory grant. And now the memory grant has popped up to 110 megs. As I pump it up a little more, 1.4 million. Guess what's going to happen? Any guesses? I didn't catch it fast enough, so we'll go over here. And, whoa, I did not want that. Hello. Tooltips. And the memory grant pops up to 128. If I go all the way up to about 2 million, the memory grant will peak at 182, which is 25% of my available workspace memory grant. And the memory grant will not go any higher than that. So even if I go up to, let's say, 2.5, run this thing again, go back over here, the memory grant is basically stuck at 182. We have nowhere else to go except to disk. Yes? The question is, how long do I have to capture the information? And the answer is that row will be there while the query is running, or while it's actually waiting for the grant, or while it's running. So once the query is gone, the information's gone. Yeah, there's nowhere else to get this information at this level of granularity. What you can do, you can look at the waiting stats, the wait stats CMV, so sysdmos wait stats. Where wait type, I think it's a wait underscore type, right? Equals resource Semaphore. There it is. And it didn't capture any because I haven't had any waits yet. But we will. Don't worry. Okay. So that's that. And the point is that there's kind of this topped out number. Now let's think about this number that we just saw. Now our total grant that's available is 91371. Our maximum memory grant is 182,736, or 22,842 pages. Okay? Now 22,842 pages times 4 is 91368 pages, which is less than 91371 pages, right? Did I do my math properly? So how many queries can we run concurrently? 4. Okay. File, open. This is SQL Query Stress, my load tool. If you've seen me speak before, you've seen it. If you haven't, go to datamanipulation.net/SQL Query Stress and download it. It's good stuff, I think. Okay, here's what it's going to do. It's going to run 100 iterations on 10 threads of this query that we just ran in Management Studio. And so it's going to load up 10 of them concurrently, and we'll see, using systemexec query memory grants, how many of them are actually running concurrently. We're expecting 4. I've just hit go. Let's go over here. There's our 10 queries. Now, grant time is null. That means that we're not running. If grant time is non-null, that means that we are running. Now, this is interesting. We're not running 4. We're only running 3. Let's go over to DBCC memory status and see what it has to say about the situation. All right, DBCC memory status. What do you know? Query memory objects. Here we go. We have 3 outstanding grants, 7 waiters. We have 22,845 pages available. Our next request is for only 22,842 pages, yet we're waiting on 34,263 pages. What's going on here? 150. Thank you. I'm glad people were paying attention to the slides. Excellent. So what we can see is that even though we have plenty of memory available, more than enough, just more than enough to run the next query, it's not going to run. It's going to sit there waiting and waiting and waiting. Now, things get even more interesting. I'll come back to that in one second. Let's throw a very large cost query into the mix. So here's a query that I've written. And this query has a huge cost, 11,479 estimated seconds to run this query. But its only memory-consuming iterator is this sort. And the input to the sort is a mere 263K. So it needs almost no memory, but it has a very, very high cost. Let's go ahead and run it. Let me make sure this is still going. Oh, yeah, we have plenty of time. So that's running. And I'm going to go back over to systemexec query memory grants. Let me just grab the SPID from here. This is SPID 52. Okay. There's SPID 52. It has not received a grant. It's only waiting on 1.1 megs. And as we just saw from DBCC memory status, there's plenty of space available, way more than 1.1 megs. It's actually over 182 megs available. but it's going to sit here waiting until that smaller queue clears out. And how can we see where these queues are? We can look over here. There's a column called queue ID, and then there's a wait order. Now, this is the only thing. This is the query that I just ran, that high cost query. That's the only thing in this queue. So it's next in line, but unfortunately, its queue is a higher cost queue than the other ones that are currently running. So those other ones have to finish. And we can sit here for a long time and wait and wait and wait. As a matter of fact, we can sit here for 86,400 seconds. And if we keep putting queries into that lower cost queue, we will wait. We can sit here for 24 hours if anyone wants to join me. Wait for that timeout. Yeah, I don't think so. So anyway, I'm tired of waiting. So let's go ahead and stop this. And let me show you how to handle this situation. What you can do is modify your workload group and set the timeout to something non-zero. So 0, again, is the one where it'll multiply that query cost by 25 all the way up to a 24-hour wait time and just sit there. But maybe I don't want my queries to have to wait that long. So what I can do is reconfigure this and say, I want a timeout after 20 seconds. Now, 20 seconds is just some arbitrary number that I've chosen, so it's fast enough so that we don't have to sit here waiting as I run the demo. I'm not telling you that 20 seconds is a good idea. You need to look at your own workload and come up with what you think is a reasonable number for this. What is not a reasonable number, however, is 0 waiting 24 hours for the query to finish, especially if you have a mixed workload where there's a lot of small queries coming in kind of OLTP style, maybe with a few sorts here and there, and then a big reporting query that will come in from time to time. That big reporting query will have to sit there waiting and waiting and waiting if you have constant load. And this is a fairly common pattern, especially with a lot of shops that are more 24/7, where a lot of small queries are coming in all the time, and then at night there maybe will be ETL queries or reporting queries that kick in, and they'll have to sit there waiting and waiting and waiting. Not a good situation. So what we're going to do is alter my default workload group, set the timeout to 20 seconds, and then reconfigure. Okay, there we go. Let me just make sure this is still running. Yes, it is, and we still have what we expect over here. Yep, we're good. So let's go back. I'm going to run the same query again, and it's session 52. And what we can see, here it is, has not gotten a grant yet, but we've only been waiting for, where's the timeout? Oh, there it is. We've only been waiting for 1 second as of the time I ran this. And we can see over here in the timeout column, they've all changed to 20 instead of based on the cost. I'm going to go ahead and run this again. 52 has now gotten its grant. It started actually running. So we're good to go. I like that. I like having my queries run when there is sufficient memory for them to run and not sit there waiting in this resource semaphore queue. By the way, an alternate way of monitoring this, select star from sys.dm os waiting tasks where wait type equals resource semaphore. And looking in here, we can see all of our tasks waiting on the nice resource semaphore grant. Wonderful stuff. Anything I can clarify on this? Yes, Klaus. Why was it now executing? Okay, so again, what the timeout controls is how long the query will sit in that queue waiting until something happens. Now, it's called timeout, and we always think of timeouts as an error condition. Something bad happens at the end of the timeout, and everything goes away. Now, in this case, it's not an error. It's actually just a queue timeout. Well, it's not necessarily an error. It's a queue timeout, which means that something has to happen when it gets hit. So after 20 seconds, a decision needs to be made. If there's enough memory to run, it'll run. If there's not enough memory for even a minimal grant, you'll get an error. And if there is enough memory for a minimal grant but not enough for a full grant, let's find out. I'm going to go back over here, stop this thing. And here is another query that I've created. And this query, like the other one, has a ridiculously high cost, $129,778. I'm actually thinking of having a contest because it took me some creativity to come up with how to get a really high cost, low grant query. So I'm considering having a little contest to see who can come up with the highest cost query with just AdventureWorks. So if anyone wants to get involved in that, let me know. But anyway, this query has a ridiculously high cost, but it's also going to have a ridiculously high memory grant requirement because there's, let me hover again, hover. Because there's a 566 meg estimated data size going into that sort. Now my entire B pool is only 1,000 megs, so clearly the sort isn't going to be able to handle that, so it's going to use everything available, every bit of Workspace grant available. And I'm going to go ahead and run it. And I'll go back over here, run system exec memory grants, and we can see 52 is waiting on a 182 meg grant. And we know there are 182 megs available, but the problem is we need 150% of that for the thing to be able to get its grant. And we can see it's been waiting for 5 seconds up until now. When I run this again, it's actually received its grant, and it requested 182, but it's only been granted 640K. Well, 640K is its required memory to run. So that's the third thing that can happen when a timeout occurs. So again, the three things are, one, if there's enough memory, the query will be granted that memory. It'll start running. If there is enough memory for just the minimum required amount, it'll be scaled all the way back and start running with just that minimum required amount. And if there's not enough memory even for that, then you'll get that exception. Now, just to let you know, now that it has the minimum required amount, if you could see my hard disk light, it's solid green at the moment. My hard disk is going insane at the moment. So this query will probably take, let's see here, its estimated cost is 129,000, which assumes it's going to do some stuff in memory. If we were to recost it with nothing in memory, I'm guessing 500,000 would be an adequate number of seconds. So if we want to wait, and once again, I'm free after this. Yes, sir. Since my timeout is 20, why have all my other queries not started? Because they're all queuing as well. Again, there's only so much memory that can run. Yeah, I mean, we can look and see. So as you can see, multiple queries have been granted the minimum amount. And these might have not been waiting. Yeah, these weren't waiting 20 seconds yet. Right. So no, so SQL query stress basically spins up 10 threads and will keep running until 100 iterations have gone on each thread. So we need to get to 2,000 before, or sorry, 1,000 before this thing will finish. So it's continually popping new queries in. And so they're continually starting to wait. Yes, sir. Good question. So the question is, if you have a special purpose machine that's only ever processing one task at a time, will it still only get 25%? And the answer is by default, yes, but you can configure that default by going into the resource governor workload group settings, and you can increase that number. And you can increase it to about 66%, after which it becomes meaningless. You can go up to 100%, but due to that 50% headroom requirement, once you go above about 66%, it doesn't mean anything anymore. It'll still hit a wall. Anything else I can clarify right now? So the question is, if there were multiple queries all running and waiting, and that timeout hit and there wasn't enough memory, would you start getting timeout errors? Yeah, if there wasn't enough for that minimum required memory, yes. But if there wasn't enough for the minimum required memory, no. They would exit the queue and begin running with only a little bit of memory. And there was a question over here, I believe? So the question is, are we page faulting at this point? Well, it's not necessarily a page fault. We're spilling to disk. at this point. Yes. And we can correlate that, and we'll get into that in just a few minutes. You go. So the question is, if the query is running with minimal memory, can it get more later? No. Once it gets grant, that's its grant. So, yeah, afraid so. So it's going to run for a while. And there was one back there? Yes. So the question is, will the timeout only help the smaller queries? Well, actually, no, it's the opposite. It'll help the bigger queries get out of the queue. Yes, they may take longer to run if there's only the minimum required memory, but they will be actually running. So I'm not telling you it's going to work in all cases. In this case, this query is going to be running for quite some time because it actually does need a lot of memory. In other cases, setting the timeout might help, but the timeout's only one option, and we haven't gotten to some of the other ones yet. So let's hold that thought for just a moment. And I think over here, yes, sir. So the question is, why was it granted so little and not some intermediate amount? Greater than the requirement, but less than the request? And the answer is because that's how it works. I don't write this stuff. Don't shoot the reporter. Okay, we'll take one more and then jump back into the slides, if there is one more. I'm sorry, could you stand up and... Is there a memory clerk? There is a memory clerk that is reported in SysTMOS Memory Clerks, GMV, but it unfortunately does not report accurate numbers. So you can look in DBCC memory status for that clerk, and you'll get better numbers. So it's called the query memory clerk. I apologize, I can't remember the exact name. I didn't put it in here, actually, because I was having trouble getting good numbers from the clerk. You get much better numbers if you look in DBCC memory status in those small query memory and large and query memory areas. All right, so let me stop this and stop my huge query over here. It canceled quickly. That's nice. Oh, that did too. Good. And cool. So we've discussed workspace memory and what it is, what happens when there's not enough of it, and so on. Well, what happens when there's not enough and things have to wait? But there's another aspect of what happens when there's not enough memory. And that's when things start to spill. And they go out to everyone's favorite shared bottleneck, as I've taken to calling it. Anyone know what that is? TempDB, yes. So it can be impossible, really, if your query is huge. If you have a 1 terabyte table and you need to sort the thing, unless you have a really, really big Superdome, you're probably not going to be able to allocate enough memory no matter what you do. And so data has to spill to TempDB in some cases. And as we saw, you can also there's also configuration limitations, physical limitations, and then there are all kinds of issues with the query optimizer. Again, cost-based optimization has certain perils that we need to keep in mind. So TempDB is our spill zone. Now here's how it works. First of all, TempDB can exist in buffer memory, but anything that spills to TempDB goes straight to disk, does not pass go, does not collect $200, right to the disk, and that's it. And anything that goes to the disk means it's a lot slower than anything in memory. So if you are spilling to TempDB, your query is going to be slower. How much slower? Well, that depends on exactly the nature of the spill. And each of the spills have kind of different behaviors in this area. Let's talk about how some of these work. So let's start with HashMatch. So how does HashMatch work? Well, it has two basic phases. It has a build phase and a probe phase. The build phase is where it takes that outer input and builds the hash table. It creates a set of what are called hash buckets, and each bucket is basically a memory location, which is a pointer to a linked list of rows. And any rows which hash to the bucket go into the linked list, and there they sit. And so the way this works, pretty simple. The input side is scanned. The buckets are created. Rows are hashed. They're put into the linked lists in the various buckets. And eventually, after some time, we have our hash table. Now it's time to do the match operation. And this is where the inner set gets scanned. The rows on the inner set are hashed using the same function as was used to hash the rows on the outer side. They find the bucket, iterate over that linked list, find the matching row or not, and continue on with life. That's how HashMatch works. Now let's talk about how it works in light of spills. Okay, so at the build time, memory is allocated based on those optimization estimates. And the estimate is based on both the input size and the probe size. We'll get into why that's important in a moment. The buckets are created in memory, and we start tossing rows in there. Now, if the grant is exceeded, some of those buckets will be sent off to the disk in order to make more room in memory and to keep things running. And this is called Grace hash algorithm, by the way. If you want to go look that up on Wikipedia, there's a great article on there that gets into really intense detail on how this works. Now, once we've built, now let's say that some of those buckets are still in memory, some of them are off in TempDB. Now we do an initial probe of the data using the inner set. And the way this works is the probe rows start getting scanned, and if the rows hash to an in-memory bucket, the match is done just like usual, and the row moves on with life. If the row hashes to an on-disk bucket, the probe row, is written to the disk along with the outer side bucket, and it's held until later. So now we have even more disk writes that have occurred at probe time. Now we go through a second phase where one by one the buckets that have been spilled over to disk are read back into memory, reconstructed into an in-memory hash table. Then the spilled inner probe rows are read back into memory, and the processor tries to match everything up. And this is where that inner side memory grant requirement becomes important, because if the memory is exceeded again, the buckets will be rewritten back to disk, and over again this will occur. And as this happens, this is called recursion. Now obviously if this keeps happening, the plan is never going to finish. So once recursion has gotten to be too much, the plan bails out. And bail out means that it basically goes right back into effectively an unoptimized nested loop where it can hit that inner table over and over and over. This means that it will use very little memory, but it might take basically forever to finish. So bailout, not a very nice thing. So, will you see the switch from a hash map to a nested loop in the execution plan? No. It's just, you will, however, be able to monitor this if you like using, there's 2 events in SQL Trace. Well, there's an event for, there's 3 events that I'm going to talk about, but the event for hash is called hash warning. And hash warning has a few different states, and one of the state is bailout. So if you monitor that event, you can actually see this as it happens. It does not happen too often, luckily. So another thing that can spill is sort. And here's how sort works. It uses the quick sort memory and starts sorting your data in memory. And it sorts it in that memory space that was allocated based on the input requirements. Now, if the memory grant is exceeded even by a tiny little bit, now this is where sort and hash are very different. Now, if hash is exceeded by a tiny little bit, just 1 or 2 buckets can go ahead and start spilling out to TempDB. Sort, on the other hand, if the memory grant is exceeded at all, the entire intermediate set will spill directly to disk, and the sort will continue on disk 100% using merge sort algorithm. So when sort spills to disk, that's a bit more of an issue than when your hash spills to disk. This is why it's important to understand the behaviors between these things. The one other memory-consuming iterator is exchange. Now, exchange iterators deal with parallel sets of rows on multiple threads. And there's 3 flavors of exchange. Distribute, where one stream comes in, multiple streams come out, Repartition, where depending on the DOP, N streams come in and N streams come out, and those N streams that come out are distributed using a different algorithm than the ones that come in. And then gather, where N streams come in and one stream comes out. And the way this works is that there are two sides of each exchange iterator. There's a producer side and a consumer side. And the sides of the iterator communicate with each other using buffers or packets of rows. And each side has DOP times 2 sets of these buffers. So you can see that for something like distribute or gather, there will be DOP sets of buffers. For repartition, since there are DOP on each side, you'll have DOP squared sets of buffers. So those things can get pretty large and use up a lot of memory. Now, they don't spill too often, but not too often at all. It's actually considered to be somewhat of a bug, or at least an edge case when they do spill. But occasionally they do. And here's how it works. The gather and repartition iterators can be merging or order preserving. And this means that if all the streams coming in are ordered, the iterators can output the data in the same order. And this works kind of like if you have 4 decks of cards and all of them have been sorted the same way. If you want to keep the order and create one bigger set of cards, you would take the top card off each set, then the next card off each set, then the next card off each set, and so on. And that's the same kind of algorithm that these gather and repartition iterators use. Now, the problem can occur if there's data skew and a lot of data is coming in, and the iterator is unable to keep things straight and keep the output ordered because the data is coming in so quickly. In this case, what it does is it spills all the data to disk until it can get things back in order. And this is called an intra-query parallel deadlock. Nice little terminology. If you use it back at the office, everyone will be very impressed, I guarantee. And you can go look it up and find out when it happens. Again, it's kind of difficult to actually even get this to happen. So hopefully you won't see this in your environment too often. If you do, you definitely want to investigate it a bit, because intra-query parallel deadlocks will greatly slow down your plan. So how do you monitor these things? Well, first of all, wait stats. SysDMOS waiting tasks. All of these spills will wait on the I/O completion wait. If you're spilling out and you're waiting on I/O completion, that's a disk wait. That means you need faster disks backing TempDB or fewer spills. Those are your choices. In SQL Trace, you can monitor hash warning, sort warning, or exchange spill events. Each of these events will fire every time there's a spill and let you know about it. And finally, you can monitor the sysdmdb task or session space usage DMVs. These have columns for user object allocations, which are your temp tables and table variables. And then they have columns for internal object allocations. And one of the things that goes in that column is anything that spills out to TempDB from Workspace Memory. So these are 3 ways that we can kind of see what's going on and understand when we have spills. So, there's a question? If max stop 1, exchange spill won't happen, that's correct, because there won't be any exchanges. Exchanges only occur in parallel plans. So if you have max stop 1, don't have to worry about it. Good reason to set max stop 1? But, you know, that's okay. Anything else before I jump into the demo? All right, great. So let's check out some spills. I'm going to jump into AdventureWorks. Head on over to Profiler. SQL Server 2008 R2. Excellent. All right, I'm going to load up a new trace here. And I'm going to show all events, show all columns. If you expand errors and warnings, you will have, somewhere in here, hash warning and sort warning. There's also an exchange spill, but we will look at that in just a moment. So I'm just going to run with hash warning and sort warning for now. We are up and running. So let's start with the sort spill. What I've written is a little simple query here to demonstrate the sort spill. And selects the top 668,935 rows from big transaction history. Why 668,935? Because it's a good number, trust me. It's going to take that number of rows. It's going to sort it and spit out the top 1,000. I'm going to go ahead and run it. And we'll go back over here. It ran. We did not get a spill. The event did not fire. So that's a good thing. And our duration was 549 milliseconds. Remember that number? Let's jump back over here. And now let's add one more number. 668,936 rows, one additional row. Well, as it turns out, that's just enough to throw us over the edge. And now we got sort warning events. Sort warning events fire on each thread in a parallel. This was a parallel plan. So we got, it was a DOP 8 plan. So we got 8 sort warnings, 8 threads spilled out to disk. 1 row difference. 1 row. Took our duration from 549 up to 1,240. Quite a change, isn't it? Something I definitely think we should think about when we're looking at our plans. What do you think? Sorry? Not as big as you expected? All right, I'd say twice is pretty bad, but that's true. Given the difference between memory and disk speed, well, now the reason it's not as big as you might expect is that most of the sort was actually done in memory. So the way it works is the quicksort algorithm starts working in memory, and it spills once it exceeds the grant, but the data can be mostly or even almost all sorted by the time it spills. So in this case, because we only exceeded it by 1 row, the data was probably just about completely sorted by the time it hit the disk. Very little work had to be done on disk. It was just dumped to disk, basically, and reread from the disk. Now, if there had been a much bigger spill, it would have had to spill a lot more unsorted data, and then there'd be a lot more subsequent work that would have to be done once that data hit the disk. So that's sort. And as you can see, that's pretty catastrophic when that happens in terms of query performance and in terms of knowing how long things are going to take to return. Hash has, as I mentioned, slightly different behavior. So let's go ahead and check that out. And we'll do top, so I'm going to select top, what is that? 3.8 million from this table. I'm going to hash join it to top 10,000 from the same table. Again, a meaningless query, but we'll go ahead and run that. And returns our number. And as you can see, we did not get our hash warning event. And our query took about 2.2 seconds. Go back over. And what I found was that if you change this to 4 million, that's too much memory. So we'll go over here, run that again. Now that time we did spill, and it actually ran faster, I'm assuming because of caching. That was not the intended purpose, but that'd be cool, wouldn't it? If we could actually spill the disk and get a faster query. So let's run it again with the spill, or without the spill, sorry. Okay, so here's the one below is without the spill. And what we can see is that without the spill, 1.3 seconds, with the spill, 1.4 seconds. Due to that Grace hash algorithm where it only spills some of the buckets, hash spill is much less catastrophic unless you hit that bailout stage, which is not going to happen on my laptop today. I ran a query that would bail out, and it took over 5 hours. The hash warning event only occurs, the bailout event is only thrown at the end. So if you want to wait 5 hours to see that demo, I figured you wouldn't. Anything I can clarify on hash? I'm sorry, why the 4 instead of the 8? Well, here is why. I think so. Basically, in a parallel query, the query grant is the same for each iterator as in a serial query, plus any grant for the exchange iterators in that query. And what happens is each iterator works independently, but works within the same memory grant requirements. If there's some data skew in there, and one iterator has a little more data than some other iterator, or sorry, not one iterator, one thread has a little bit more data than some other thread, then that thread will spill, whereas one of the other threads might not. So if we go back here, and we turn on actual execution plan, Let me put back 4 million. Is that right? Yeah. Okay, we'll let that run. Let's make sure we still got our spills. There's our 4 spills. We'll go back over here, and coming into our hash match, we'll hit F4. And what you can see is that the actual number of rows is not quite even across these. You can see that we have about 4 rows here, 4 threads with rows kind of in the 4.8, 4.9, and then we have these threads in the 5.1 range. So basically what happened here is those threads with more data spilled, and the threads with less data didn't have to spill. So again, it's a thread by thread kind of thing. Yes? The question is, did they exceed memory limits? So yeah, they've exceeded the grant. So the grant is split up across all the threads in the parallel plan. And so they exceeded it, so they spilled. So, all right. Now one other thing we can check out while we run this is wait type equals IO completion. If we start this again and I'm fast enough, which I was not, we should be able to catch the spill. Well, I'm not fast enough, so we won't. That's still running. Interesting. You know what? I ran the entire script. That's why I didn't catch it. Anyway, let's look for SysDMOS wait stats. Okay, so I couldn't catch the real-time one, but if you have a slow disk system, as I do in one of my projects where it takes 300 milliseconds for each disk request to go right out, you will see these in SysDMOS wait stats. And when you see those long-running things, you will know that your query is going to return very, very slowly. And as you can see, we had a ton of these things. And this is my laptop, which I just booted up just before coming in here. And we've had quite a tremendous wait time on I/O completion just in that little period. So you definitely want to monitor this stuff. Sir. Is anything else going to I/O completion? Yes, there's a few different things. So not too much, though. Most of the time when I see I/O completion on a live system, this is what it is. One of the other things is like copying the model database, and there's a couple other things. I don't recall them offhand. Okay, so I wanted to show you one other thing, which is intra-query parallel deadlock, just because it's fun to say. So I actually couldn't come up with a demo of this on my own because it's so rare and so difficult. But there's this guy named Paul White. He's known as SQL Kiwi if you're on Twitter. And Paul is one of the smartest guys in the SQL Server world right now. And he's insane as well. And he'll sit there and pound away at a problem for like days on end until he comes up with a demo that works. And so he actually was nice enough to do this for me. And he came up with this crazy table and this crazy query, which involves about 1 million parallelism iterators. So there's 1, 2, 3, 4, 5, 6, 7, 8. There's 9 parallelism iterators in this little query. And if I go ahead and hit stop, go to File, Properties, Event Selection, and if I scan for Exchange Spill Event and scan for Deadlock Graph, let's do that. Deadlock Graph, where is it? Sorry, deadlock chain. Thank you. I'll just do the chain. If I run that, and then I run this query, and we stand back for a minute, what we're going to see, let's go back over here, is we're going to start spilling and deadlocking. So the query is actually deadlocking with itself because data is coming into that final parallelism iterator, and it's a merging iterator, and it's coming in too quickly. Now, if you want to see whether or not it's a merging iterator, you can go over and hover over it, and at the bottom, you'll see that it has an order by. If it has an order by, it's one of these merging iterators. So if you're seeing these intra-query parallel deadlocks, look for the merging iterators, and you can figure out where that issue is occurring. and what's going on. So anyway, hopefully you won't have to debug that situation. Anything I can clarify on these before we jump back? All right, cool. For those of you walking, by the way, this is a 90-minute talk, so we have 15 more minutes, unless you're really bored, in which case, go ahead. Are we back? Yeah. So we talked about not enough memory. Now let's talk about balance. That's really our goal here. We want all the kids to play nicely together without having to fight too much. So we have two issues at hand. We have the issue of too much grant. Not too much grant for the query that's running now, but too much grant for all the other queries, which means that the query we run now doesn't have enough grant. Well, that's not good. It's a concurrency impact. Then we have the too little grant, where everything goes to disk. And what we need to find is a way to balance between these things. Maybe allow some things to go to disk, allow other things to run, and hopefully we can find a middle ground that works for everyone. So as far as not enough grant, we have two primary sets of problems. Incorrect costing, based on bad statistics or something along those lines, can create a bad estimate. We have something called the out-of-model scenario. Out-of-model is anything that we put into a query plan that the query optimizer isn't set up to handle properly. And there are several of these things, including various features in SQL Server that you might have used. We need to avoid these out-of-model scenarios if we want to get good estimates. Parameter sniffing. If all of your data, if you have 1 million rows of data about the United States and 1 row of data about Canada, and the first request that comes in is for Canada, you might wind up with a cached plan based on estimates for Canada, when all your other queries that come in for the US will get those same numbers and won't be able to get the correct memory grant. And then we just have generally the problems with cost-based optimization. It's not always going to give us the right answer. The second kind of set of problems is just not enough memory. Straight up physical memory limitations, configuration limitations. Sometimes there's just nothing we can do about these except rewrite our queries in a different way, think about things a different way in order to do a better job. So how do we fix these problems? First of all, try recompiling the query. The option recompile hint is your friend. It's very, very useful in keeping parameter sniffing problems at bay and making sure that things are a little bit more stable. I think that a lot of us from back in the SQL Server 2000 days were kind of afraid of recompilation. It used to be very CPU-heavy operation. It still uses a lot of CPU time, but for specific queries, very targeted scenarios, it can be an incredibly useful tool. Next, try rebuilding the statistics on your table. Doesn't always work, but sometimes it'll help with this issue. The worst out-of-model construct that you can use is a multi-statement table-valued function. If you have a multi-statement TVF that returns 1 million rows, how many rows is it optimized for? 1. Always 1. Therefore, you will have a memory grant of 1. Always 1. That does not spell good performance. Avoid like the plague. If all else fails, last resort, use option optimize for and tell the query optimizer what it should do. If you don't have enough memory, either break the query into smaller chunks or go to the electronics store and buy some new RAM and go slap it in your server. Your choice. Too much memory. This spells queries sitting there waiting, concurrency goes down, everyone runs around screaming and yelling. It's a bad situation. We want to avoid it. So how should we avoid it? First of all, once again, check for bad estimates. The option recompile and the bad statistics problem goes both ways. Not enough or too much. Recompilation is really the only way to keep things stable in a lot of cases. Variable linked data types can be very dangerous. What is the estimate? Let's say that you have a varchar 4000 column, but every value in there is a single character. What is the estimate going to be? Does anyone know? For average row size? Anyone? So it's varchar 4000, so it's going to be 2000. Varchar and other variable length columns are estimated at 50% of the defined size. The estimate has nothing to do with the actual data size. So if you have one of those people who designs databases by putting varchar 8000 on every column, you might want to rethink that. If you create first name and last name columns of 200, just in case some guy from Mars happens to visit, you might want to rethink that strategy. You're causing your estimates to balloon, and you're actually hurting concurrency by having a bad data model. Kind of crazy to think about it, but it's true. Resource governor. If you have some of those high cost but low grant queries that are sitting in the queue, if you know where they're coming from, if you're able to categorize them into a workload group, create a pool just for them to play in. And then they won't have to wait behind all of the other queries playing. If you want to improve concurrency across the board and you don't mind taking a bit more disk hit, maybe you have solid state disks back in TempDB and you can afford this, consider limiting that grant percentage in resource governor. Now remember we talked about dropping the timeout so that queries get through, but then they hit the disk if they don't have enough memory. Well, you can balance things a bit by dropping the timeout and limiting the grant percentage both so that there will be more memory when that timeout gets hit and things can get through and start playing and finish. And finally, once again, option optimize for. I'll show you how to use it in conjunction with top to impact the estimates, the row count estimates that come through and start really playing games with the query optimizer if you feel comfortable going to that level. So let's jump out. How much time do we have left here? 7 minutes? I think we can do it. Okay. So, I'm going to jump out to AdventureWorks, and I think I still have my sort warnings here. I'm going to go ahead and run this query. This is kind of a funny query. I'm going to include the actual execution plan. Okay, actual execution plan. Our memory grant was 55 megs, which is less than the 182 megs that my maximum grant should be. But I had a sort warning. Why is that? Because the query optimizer did not think that as many rows would come through as did. Actually, the number of rows was fine. It was the data set that was different. The optimizer was estimating 35 bytes per row. Maybe there was a bit more than that came through. I have updated statistics on this table just last night. So this isn't a statistics problem. This is just a standard problem where the query optimizer was not able to come up with a great plan for this. Now this goes into a sort. That means that the query is taking twice as long as it needs to take just because the query optimizer doesn't have the right answer. I don't like that situation, do you? Well, at least not in my databases. Okay. Now let's take out a quick out-of-model situation. I already described this. I'm just going to create a multi-statement UDF. It's going to return a table called history rows, 600,000 rows in there. I just created that. Let's select from it with an order by. And guess what? We are only going to sort, as I mentioned before, one row. Let's run it, and this thing's going to be spilling all day long. It actually ran pretty quickly, given what it had to do. But it ran for 10 times longer than the previous query, even though the same amount of data was sorted. That's a great example of the optimizer just, it's out of model because the optimizer can't see inside that TVF. Has no clue what's going on in there, doesn't care, says, whatever. Not a good thing. Okay, so avoid those. How about our varchar 8000 situation? So here we have varchar 8000 with one character each. The character is A. Let's select. Where do we go? Oops. Let's select all the rows from our temp table. We'll increase the size a little bit so I have time to get over to another window, and we'll order the results. And while that's running, exec query memory grants. Okay. Hit F5. Okay. There we go. Now we have been granted 182 megs, but how much was used? Only 19 megs. That's a big waste of memory. This kind of thing happens all the time. I mean, that's a huge amount of memory that could be used for much better things than being arbitrarily granted to this query just so it can be thrown out. Yes, sir. How does row compression affect it? Not at all, because by the time it hits the sort iterator, it'll be uncompressed. I'm going to hold the questions because we only have 5 minutes left. Apologize. Okay, so there's a couple of different ways we can kind of start fixing these problems. First of all, here's a query where I've wanted the top one product ID based on actual cost. Top one row. So I want the row for each product that's sold for the highest cost. So I'm doing this with row number, partition by product ID, order by actual cost descending, where actual cost is greater than 5,000. Out here, I filter where R equals 1. So I'll get that number, that top row. And let's see what this thing does. Has a couple sorts and some other stuff. And what we need to do, if I run this, it'll take a couple seconds to run. And I want to start rethinking how I can deal with this problem and what the problem is. And actually, that's taking a tremendous amount of time to run. The problem is this query needs to do a number of large sorts. It takes all the data in. I'm just going to stop it. We'll say it took 20. We'll pretend it finished in 21 seconds. Oh, it's taking forever to cancel, too. Wonderful. OK, let's go back over here. OK, so let's look at this query. And it has to sort this huge number of rows. And then it segments them. And then it has to sort a smaller number of rows. Well, each of those sorts is going to require, especially that first one, is going to require a big, huge memory grant. And all sorts of spills occurred as a result of that thing. So let's go back over and think about how we can break this up into smaller sorts. And here's a method that I've been using quite a bit in the last couple of years. Rather than sort the big table once, I add a new table into my query. So here I'm taking the big product table, which has a 1 row per product ID. I'm using cross-apply, and I'm correlating into the operation on the product ID. And now I do my sort just for each product ID. So for each product ID in the outer table, I do a seek into the inner table, do a small sort in that inner table, and I return the same exact information as before. But let's look at the new plan. So now we scan the small big product table, seek against big transaction history, and then do a very small sort of an estimated only 448 rows per sort. Now that's never going to spill. It's never going to have to spill. So when I run that, rather than running in 28 seconds or however long, we'll let that run for a moment. Watch, it's going to take like 35 seconds. Actually, it runs significantly faster when my laptop likes to work for me. While that's running, since we're running very short on time, I want to talk about hacking top. So the query I was running above was select top 600,000. Oh, that's still running. I'm just going to stop it. So you can run that demo on your own computer. I promise it'll be faster. So this one was select top 600,000 from big transaction history, and we saw how that spilled. If we wanted to give it a little more memory, we could influence query optimization by hacking top. So here's what I'm going to do. Declare a variable called @I, set it to 600,000, and then I'm going to select top @I rather than top 600,000. And I'm going to optimize as though I were bringing back 650,000 rather than 600,000. So now I'll have a 650,000 row memory grant rather than the 600,000 row memory grant that I got before. And when I run that, it runs pretty quickly, and I do not get any kind of spill at all. So that's one way of eliminating the spill. Another thing we can do, we can fake a set of input rows bigger than the one that's really there. And here's how we do it. I'm selecting my 600,000, and then I'm union all with the 50,000 more rows from big transaction history where the variable @I is 1. But @I is 0. However, I'm telling the optimizer, optimize as though @I were 1. So now I'm going to get, once again, a 650,000 row estimate for my 600,000 rows at runtime. Now, I've been accused, when I use this, of writing unmaintainable code by a customer. But I said, well, okay, would you rather have your query in an hour or 5 minutes? And they saw the light. So make up your mind. If you don't like it, don't use it. But the other thing we can do, remember this query used the maximum amount, and so it didn't run very concurrently. Well, if I wanted to bring down that maximum amount, I could use top the other way. So here we have top 2 million, and there's no reason I can't limit things and do top at I optimized for 100,000, for example. And this would allow more of these queries to run. And I've actually used this several times in real customer scenarios when we had a bunch of the same query all running using a ton of memory. I threw this in and I optimized them all down a little bit so that more of them could run at the same time. We weren't able to categorize them into resource pools in a nice way, so sometimes you have to play games. The other option, of course, is to change the resource memory grant request. The default is 25, but I could change it to 10, 12, 5, whatever, and put a hard limit on memory grants in that way. So we are just about out of time, but just wanted to say, too much memory, not good. Too little, not good. So strive to take the middle path. Balance Zen. Thank you.